It is time to continue the story that we began in the previous lecture. Our story, which left off at the following cliffhanger. We had taken a simplicial map F and used it to build what was called a chain map that related the chain complexes associated to the domain and codomain of our chain of our simplicial map. And now the question is, what happens at the third leg? Whether we can use such a chain map to extract reasonable notion of maps between homology groups. So let's get to work on that. Here is the result. If you let phi be a chain map between two chain complexes, which I'm going to write as C and C prime, then it induces, by it I mean this chain map phi, well-defined maps. So well-defined linear maps, which I'll call HK phi, going from the homology of the source chain complex to the homology of the target chain complex. And this is true for every dimension k bigger than or equal to 0. Now, I guess this might sound strange until we explain what induces well-defined maps means here. Well, all it means is that phi k sends the kernel of dk to the kernel of dk plus dk prime, and the image of dk plus 1 to the image of dk plus 1 prime. That's what this means. And if you have two spaces and the homology is their quotient, and your map sends the numerator to the numerator and the denominator to the denominator, then it descends to a well-defined map on the quotient spaces. Okay, so this is what we'd like to prove, and let's do the kernel part first. So let's assume that gamma belongs to the kernel of dk. Now, what we want is to show that phi of gamma belongs in the kernel of dk prime. So let's check what dk prime of phi k of gamma is. Well, by the defining property of a chain map, this has to be the same as first taking the boundary of gamma in the chain complex C, and then applying the chain map phi. But this, well, in degree k minus 1, but it's not going to matter because gamma is in the kernel of dk, and the minute you hit it with dk, this gives you a 0. So that whole thing gives you a 0, which means that phi k of gamma is in the kernel of dk prime, as was promised. Now let's go to the next stage, which is for the images. So if xi is in the image of dk plus 1, then there exists something in the k plus 1 chains whose boundary gives you xi. So there's some xi hat, so that when you attack it with the k plus first boundary operator, the chain you get is xi. That's what it means to be in the image of dk plus 1. Okay, now let's see what happens if you look at phi k of xi. And the claim is that this thing, phi k of xi, has to be in the image of dk plus 1 prime. That's what we want to show. Well, there's not much to do here. So you have phi k, and xi you know is dk plus 1 xi hat. By the defining property of a chain map, you can switch the d and the phi at the cost of messing around with the indices. So this is going to be dk plus 1 prime composed with phi k plus 1 of xi hat, which is clearly in the image of dk plus 1 prime, as promised. So that's it. It said phi k is going to send your kernels to kernels and your images to images, and therefore it produces a well-defined map of homology groups. And that is what goes over here. in the third piece of the arrow. So HK of C is what goes here, and now you're in good shape. So a few points to note. A is when phi comes from a chain map. When phi comes from a simplicial map, which is to say that phi is C of F for some F K to L, then we compress notation. Then we will write the induced map on homology by phi is going to be, so instead of writing H of C of F, instead of that, we'll just write H of F. And this is going to go from the homology of K to the homology of L. So just a shortcut there. Anytime you say H of a simplicial map, you really mean H of the chain map induced by that simplicial map. So that's a minor shortcut. The second thing to keep in mind is computation, which is that when the chain groups are all finite dimensional and you have a chain map, then you can actually express these induced maps on homology, these HK phis, as a matrix, which is to say this can all sit on a computer and it's nice and computable with linear algebra. This would require 3 steps. The first one is to get bases, so basis vectors B, K for the kth homology of C, and BK prime for the kth homology of C prime. And you can get these basis vectors by using the Smith normal form, as was discussed in week 3's lectures. B, you want to express the image of each basis vector. So this is going to be a set. You apply, you attack every basis vector in BK with phi, and that's going to give you some matrix. But all of these things are going to land up in the homology group HK of C prime, which means you can always write them in terms of the basis BK prime. And one way to do this is to build a block matrix which has BK prime in the first block and then phi K of BK in the second block, and then RRE, reduced row echelon form. So this will let you express everything on the right side in terms of linear combinations of things on the left side. And so this will basically give you a matrix representation for the induced map on homology for any chain map, provided that all the chain groups are finite dimensional. So in particular, anytime the chain map comes from a simplicial map, you have the ability to write it as a nice matrix. Okay. There's something important to note, and I guess I'll say it in the form of an example. Induced maps on homology can be subtle. What I mean by can be subtle is it's not enough, just as with functions. If you have 2 topological spaces that are homeomorphic, it's not necessary that every continuous map between them will realize a homeomorphism, will be a homeomorphism itself. So what I mean by can be subtle is, okay, so this computation that we've talked about, there's no shortcut to it. You can't just stare at a simplicial map and figure out what action it's going to have on the homology groups. One example is if you take the inclusion of the hollow 2 simplex, which I'll just write ABC here. This goes to includes into the slightly larger simplicial complex here, but let's say we add a 2 simplex there. Well, both these And so this is your map, simplicial map F. So let's call this K, let's call this L, and F is just the inclusion A to A, B to B, C to C. So both K and L have homology, which is F in dimension 0 and 1, and 0 otherwise. And you can compute this using linear algebra if you like. But the first dimensional homology map induced by F is not an isomorphism. And the reason for that is if you look at the domain, the first dimensional homology is generated by some linear combination of these three simplices. That's what's giving you a one-dimensional cycle. And those three go over here, and they still create a cycle, but the trouble is that cycle is also the boundary of the two simplex, ABC. And so that's going to just get killed when you look at the homology. It's going to be in the quotient space. And of course, the reason these two simplicial complexes end up having the same homology groups is that there is a good cycle in L, but it's not the one you hit with your map. So, F is not going to give you an isomorphism on homology. Now, if you had sent the vertex B to the vertex D, if you'd sent the red stuff to the blue stuff on the right, then everything would have worked out just fine, and F would have been a simplicial map. So we have to be a little bit careful about how things work. Okay, so here's a proposition which I'm not going to prove here. It's the chase your definitions type of proposition, but it does have important ramifications. This is called the functoriality of homology. And this is what it says. I guess there will be two steps to it. The first one is if F is a simplicial map from K to L, and G is a simplicial map from L to M. So K, L, and M are simplicial complexes. Then the chain map induced by the composite G composed with F is the same as the chain map of G composed with the chain map of F. So, which is to say, if you this assignment of chain maps to simplicial maps respects composition. If you compose simplically and then take the chain map, that's the same thing as first taking the chain maps and then composing. And B is the same story, but for chain maps and induced maps on homology, which is if phi and psi are chain maps, that's a double prime, are chain maps, then the induced maps on homology satisfy exactly the same type of relation. You can compose a chain maps and you get a big composite chain map from CD to C double prime, D double prime. Or you can first take the homology and then compose. And it doesn't matter which of those two things you do because it's going to end up giving you exactly the same answer. And this is an extremely important property of homology that makes you, it allows us to use functions, linear maps between homology groups to sort of see what the action of any simplicial map is in terms of homology. So it's a lovely and important theorem. And if you want to prove this proposition here, then you just apply the definitions and see that, it's a slog, but it's a useful slog. So if you haven't ever done it even one time in your life, then you should do it exactly once in your life and then never do it again.